Hello everyone. Am I audible?
Yes, sir, we can hear
Yes,
you.
you are audible.
Okay. So, everybody has went through the like seventh week content.
Yes, sir.
So I guess Saturday is the deadline for submission, right? But the questions I guess in the graded or practice are not that difficult.
Excuse me, sir.
Yeah.
Sir, can you discuss lecture 7.1? I think the sir that did not derivations for the PCA.
Okay, I'll
Actually,
go through that. So my voice is clear, right? I'm
yes,
having some
just give me.
throat
Yes, sir.
issue, so yeah, you have to manage. I guess. Yeah, P2 the audio is not clear, or
It's quite
Yes,
muddled,
you are
sir.
audible.
But if you can be slightly louder, it will help.
You are
okay.
audible, sir, but you are.
Hello. Yeah. Okay. So I'll start with which one? First lecture. Okay. So I've shared that book. Have you went through that page number I told you, like 561 to 565? That page number of that book. That one book that I shared on the discourse. Has anyone went through that? So basically, those I guess the faculty, like the professor, has used the same book, I guess, to discuss the proofs and all of the PCA. The basic maths behind the PCA, are you aware of that? Like, is it clear? Like, whatever we have discussed in the last lecture?
Yes, sir. In the previous one, right? About the we were looking at which characteristics we will choose
Yeah. So that is
based on
clear, right?
variance. Yes, yes.
So last lecture we have discussed like basic maths. Why are we doing the PCA and what are the final results, right? And I told you to know how is it coming, you have to go through the lectures, right? So we'll see that how that professor has went through the proofs and all. I'll take the help of the book also. That one book, yeah. So Preto they has shared in the chat box also that book. If somebody was having issue, you can go through that also. I guess that is what like professor has taught in the lecture. Okay, I'll just share my screen. Okay, so okay, so this is what has been discussed by the professor, I guess, right? So what he has started is so where are the doubt like in which uh, line or which where generally you have the doubt? Like one guy was asking Harshdeep, I guess I can't I forgot
Yes,
it.
sir. Actually,
Hmm.
can you scroll up?
Okay, so okay.
Yes, from that part. Yeah,
Okay,
next
so
step.
okay, this one.
Yes, from that part over.
Okay,
Mm.
okay. So see, I'll start from the beginning. So the problem statement, the feature, this is simply a feature selection. Okay, so start with the main as many features as you have. Okay, audio is not clear. Is it? Oh, it clear now?
No, sir, you are not
No,
audible.
sir.
Okay.
Yes, now
Okay.
can you
Now it's
speak
fine,
again?
right? Yeah, now it's fine, right?
Yes, I think.
Yes, sir.
Okay. So the PCA, in the PCA, see, this is the book, I guess. Not this one. So yeah, this is the book from where I guess the reference has been taken. Okay. So there are basically two methods by which you can have the proof or the you can understand the maths behind the PCA. Though we have already discussed the methods, like you can go with the either you should go with the you should get the direction where the variance is maximum, or you should go with the direction where the direction of the vector where you are getting the reconstruction error as minimum, right? So two methods are there. The first one will start with the variance, the maximization of the variance. Okay, so I'll discuss this the whatever the professor has started. So the first one he has discussed is the minimum error formulation. Okay, so what he did, so this basically the main idea is to decrease the dimension or decrease the number of features, okay, out of whatever the features we are having, so that we have a less number of less number of features, so that we can visualize those features basically, right? So or to minimize the time complexity of the algorithm. So this is the main two basically. So this PCA is basically very old method, like I guess this was developed in 1960s or 70s. Nowadays we are having a like algorithm, but this also generally we use. Okay. So one more thing. So have you went through the lecture that I told you that was by the professor uh, Arun Kumar? Uh, so that lecture you can find it on the YouTube itself. So that has been uploaded on the YouTube. Okay. So, so that lecture, I guess where is that? Okay, I'll tell you in the end, I guess. So, okay, I'll just search that piece.
Sir, can I ask something here?
Yeah,
Sir has given these 2 points: reconstruction error and variance, maximization of variance.
yeah.
So what I can understand from the variance of the projected data is maximized, so that
Hmm.
the variance is maximum, so that we can reach to the maximum data points that are available, isn't it? Is it?
Maximum data point. The reason behind we are taking maximum variance, like the direction where the variance is maximum, that I'll tell you one example. Okay, maybe that will clarify that. Okay, I'll just go through the same slide that I used in the last section. Okay. So this is the example that I have discussed in the last. So why we are choosing this variance as the direction where the variance is maximum. Like for example, I'm having the same example I'm taking. Uh, so I'm having a data set, right? And I'm having a data set that I have collected from some 1,000 Indians. Okay, and that the data set I'm having the features, whatever I'm having, the features F1 and F2, I'm having two features, okay, that I have collected. And I need to use this algorithm to predict something. Like, for example, I taken height and blackness of the hair, right? So the blackness of the hair will be having very less randomness, right? Because the blackness, if I'm taking collecting the data from some 500 people or 1,000 people, the color of the hair will be almost same, right? Are you
Yes,
getting me
sir.
right? Okay,
Yes, sir.
so like for example, see, here is the spreadness. This is the feature one, that is the blackness of the hair. Okay, so what would be the mostly the color of the hair in India? Mostly, I'm not taking the red and what are the blue colors and all. So mostly the people would be having gray to black color, right? So that if I have to normalize those value in some mathematical form, I'll convert that. That value will be from, I guess, 0.9 to 1, right? Maximum, like this would be a maximum, that dark gray to a black color, right? So this features, like for example, I'm having features one as the color of the hair, and the F2 is the height of the person. I need to predict the weight of the person. Okay. So if I'm having this features one, you will see that for all the 1,000 peoples, I was having the same data, like the value, right? For one features. So almost every time writing 0.9 or 1, 0.9 or 1, almost every time, whatever the data I have collected, I can see that the spreadness of the data in features one is very less. Okay, so I can remove these features, right? Because to know the weight of the person, okay, this thing was not helping me, because every time if I've generated one algorithm, okay, so x1 plus some f1 plus x2 plus f2 plus some constant. So every time this f1 was coming same, right? So the algorithm, whatever we were using, for example, some basic algorithm we were using, okay, so linear regression only I was using. So if that algorithm will see that every time the f1 was same, right? So I can remove, even I'm removing this f1, the weight will be mostly based on the height of the person. Okay, so this features is not helping me. Okay, so what I have concluded from here, wherever the features is very less or the spreadness of the data is very less, that features can be excluded from our algorithm, right? So which direction we need? Now we are needing the direction where the spreadness is very high. Like for example, here I need f2 only. Why I'm needing f2 only? Because the spreadness of the data, like here the features f2 was height, so the spreadness of the features height is most in this direction, right? So that's why I'm needing that direction only. Are you getting my point?
Yes, sir,
So
yes, sir.
the
So
basically that's the, yeah.
basically the feature that is varying the most
Hmm.
will be useful here, and the other one which is not varying is not in use.
Yeah,
Is
not
not
in
of much
use.
use actually, much use.
Yeah, so that can be excluded. Okay, so what I'm doing here, I'm just taking f2 to predict the value of my weight. Okay, so this is the basic example, the most basic example. And why I'm doing this, I just want to convert this 2D into 1D. For example, I'm not able to visualize 2D, just for example I'm telling you. So I want this feature, this 2D into 1D, so that I can visualize it. Like for example, I'm having 10 features I was having earlier. Okay, and I want to convert that 10 features to 2D, so that I'll be able to visualize those features, right? So 10 features, out of those 10 features, the if I'll apply that PCA, what PCA will do, with the combination of that 10 PCA, it will try to convert those 10 features into 2 features only, and that 2 features will be having maximum of the most of the information will be consisted in this 2 features only. Are you getting my point? Like, not directly we are removing. See, for this example, I've directly removed the blackness of the hair. Okay, I'll show you this example. Right, for example, I'm having this features f1 and f2. Okay, again I'm having 2 features, but the data set whatever I'm having is not directly like with just with the seeing, we can't say this f1 which one to remove, whether f1 or f2. So for those cases, what we'll do, we'll just find this direction. Why this direction? Because in this direction, the variance you can see is the maximum, right? In f1 dash, if you see this f1 is the one feature, sorry, f1, this f1 is one feature and f2 is the other features, right? So what I'll try to do, I'll try to get this f1 dash and f2 dash that is orthogonal to each other. Okay, as I was having 2 features, so I can get 2 eigenvalues. Like for example, I'm saying, so I'll get 2 eigenvector, and that eigenvector is would be orthogonal to each other. Okay, so this direction, this direction I need. So this f1 dash direction, why I'm needing this? Because if we'll see that the spreadness is from here to here, right? From here to here, the spreadness of the data in this f1 dash direction is from here to here. But if you see in f2 dash, you can see the spreadness of the data is very less. So what I'll do, I'll remove the f2 dash. F2 dash I'll remove. I'll keep only f1 dash. Okay. So after root, like
if I need this F1 dash only, so I was having F1 and F2. So with the rotation, some sort of things I'll do so that I'll get F1 dash. And if I'm able to get F1 dash, I'll just keep F1 dash. That I'll try to give it to the algorithm to predict the value. I'll not give F1 and F2. I'll just give F1 dash. So what happened? We have just converted 2D into 1D. Okay, so that will help us to visualize also, and will help in time complexity, like reduce the time complexity of the algorithm, whatever we are using. Have you got the point? And one method, whatever you were saying, so that can be like basically correct if like for example there is other method also to decrease the reconstruction error or the error so the how will you remove, like either to increase like the maximize the variance or to reduce or the minimize the this what you can say the error. How will you calculate the error? So you already have the data set. You need to find that direction where the if you'll project the data set, okay, after projecting the data set, you'll calculate the error, and the error should be minimum. Okay, so this direction you'll get in those cases also. So both are same method, only like in the end you'll get the same final value, but those two approaches can be seen, right? Either to maximize the variance or to reduce the error. Is it clear?
Yes, sir. Sir, one thing, SVD and PCA both are reducing the dimensions, isn't it?
So SVD is what we are doing. In the end, what we are doing, see, PCA is generally, I'm having some 1,000 features, right? So like, for example, I'm having 1,000 features. Like I told you one example in the MNIST dataset. MNIST dataset, I was having some 60K dataset, like the training dataset. And the features I was having 786 features. So this is the matrix of what? 60K cross 786, right?
Yes, sir.
So this is a rectangular matrix. Okay. So see, the final result what we are getting PCA is the final result we generally get is the whatever the matrix we were having in the starting. Okay, like for example, you are having some rectangular matrix of M cross N. Okay, so what you will do, you'll calculate the like what the matrix, the data set, the matrix that you have calculated. Like for example, here it is 60K cross 786. So you'll calculate that in SVD. How generally you calculate that eigenvector, eigenvalues or eigenvector. So you generally do that A transpose A. Okay, so A transpose A2 you calculate and then calculate the eigenvalue of those A transpose A and then calculate the eigenvector. Okay, so here also what we need. So this direction is what? This direction that whatever we were needing. Okay, so if you this problem, whatever we were like, this problem we have to solve, this mathematical problem we have to solve, and then we'll be seeing that in the end, whatever we are getting, this direction was corresponding to the eigenvalues, the maximum eigenvalues that we were like able to calculate. So this direction was corresponding to the eigenvalues. Like I'm getting some land, like for this example, I was having F1 and F2. So I got eigenvalues, some sort of like 10 and eigenvalue 2 as 1. Okay, so this variance where the variance is maximum, will see that the eigenvector corresponding to that lambda 1 will be of this direction. Are you getting my point? So this SVD is somewhat helping us, like when we're able to calculate that covariance matrix. So we need to know regarding the eigenvalues of the covariance matrix. So SVD, why we learn just to know how will we calculate the eigenvalue, eigenvector of those cases. Okay, when we're having a bigger chunk of like if we are able to, like for example, we have studied from the spectral theorem and all how to, if we are having a bigger matrices, so how will you get the other matrix? Okay, that will be almost similar to that. So that I'll be able, if I need to calculate anything regarding those bigger matrices, I'll just calculate on the similar matrix. Okay, so here also we are doing the same thing. We are having some bigger matrix, so we have calculated A transpose A, and from that A transpose we have calculated the eigenvector, and that will help us to know the eigenvector corresponding to the eigenvalue, and then we'll be able to know the direction that we are needing for the PCA. I hope this is making a bit clear, or it's not.
So we are using SVD to conclude PCA.
Yeah.
Okay.
So we are taking help of SVD. Okay, SVD is totally mathematics, right? So PCA is a basic algorithm in the unsupervised algorithm in the what do you can say, and
So
supervisor
is it preferred? Is it preferred that we should be using SVD? Is preferred over that matrix, covariance matrix?
So generally we are calculating that covariance matrix, right? Okay. So this is basically what, if somebody is not knowing SVD also, he'll be able to solve this, because I'll tell you that, like, if I'm able to directly tell him that just calculate the covariance matrix, okay, and then calculate the eigenvector of that covariance matrix. Okay.
But sir, I think that will become a little tedious, and will SVD give a more intuitive view to that? Like,
Yeah.
since we can
So
do
that's
like
why,
X transpose X.
yeah. So whatever the matrix we were having in the starting, like the bigger matrix, okay, so that can be, we are able to solve because we already know about the SVD. That can be solved without knowing that also, because when I read first time the PCA, I was not knowing about the SVD. Okay. So because at that time I was not aware of the maths also, like the basic maths I was aware, and I need to use that simple library, that PCA library. That's it. One line of code and you'll be able to do everything. So there's no need of that. But okay, you have to know the basic maths if you're somebody Dutch wants to know. Like, you can apply this PCA totally with your Python program also, or with the help of one line of code also. In the Python program, you have to go through all the method, how generally you calculate. So you have to calculate all the data set. You have to calculate the mean, and then calculate the covariance matrix, and then calculate, and then you'll end the eigenvector, eigenvalue, and then in the end you'll be able to do. But in the, with the help of one line of code in the, what you can say, sklearn, you'll be able to directly know the best two features. There are other methods also. There are so many other methods to eliminate the features. Like, for example, if I'm having 1,000 features, so I'll just run one basic RFE to know the best two features that will help me to know the final result. If I'll just apply some logistic, like some algorithm with some basic uh, elimination method of the, what you can say, the features, and I'll be able to know. So, but okay, those things you'll be reading in, I guess, when you will be doing the practical coding and all, MLT, I guess, and the techniques in the next time, I guess, you'll be reading about those things. I don't know PCA you'll be using or not, but those methods you'll be using in that. PC is generally a very old method. So nowadays, generally people don't use, like, there are other good methods to solve like this type of problem.
So now I understood little bit, because I was having a confusion between SVD and PCA. Like, what was SVD doing? That was also reducing the dimension. PCA is also reducing the dimension. So I was not having that
But
understanding of what was
SVD is
happening.
not reducing dimension. SVD is simply the basic, like, why we have read that SVD just to conclude the PCA only. Like, if I'm solving some problem, so SVD is going to help me in the end. That's it.
So then what is decomposition? What does decomposition mean then in that case?
Where the decomposition? Okay, so that
Like,
rectangular matrix is that you are, okay, that thing
yes,
you're
yes.
asking. Okay, where I need to open that slide once. Okay, this one.
Yes, sir. Yes, sir. This one, M is equal to U sigma V transpose. So this is somehow we are decomposing the matrix M into those components, like.
Yeah, so this is what we are, like, PCA is getting help from the SVD, right? So if I'm having some matrices in the form of rectangle, okay. So earlier we were not aware how will decompose any matrix that is in the form of, that is not in the form of square, right? So SVD is helping us to decompose even the rectangular matrices, right? SVD is what SVD is
So
helping us.
basically,
Yeah,
SVD is a tool to reach to PCA.
yeah. You
Is it?
can
We can.
conclude this. Yeah.
I can put it that way. Okay,
Yeah.
okay, sir. Okay, thank you, sir.
Okay, so somebody else has raised, who is that? Uh, okay, so where was I? In the first, I guess, lecture, right? Okay. So the one thing is that the PCA you can conclude with the help of both the method. Either you are doing with the reconstruction or the variance, maximizing the variance or minimizing the reconstruction. Okay. So So on the first we'll go through the reconstruction and how the professor has went through that. So he was having a data set of like n. Okay. So we are having a one data set. So like, for example, we were taking in the MNIST, we were having 60K. So here also the data set is like n. Okay. So project D onto M dimensional, that M should be a smaller. Like we were concluding from the 2D to the 1D, right? So here the professor is doing from some bigger D to a smaller M. Okay. So it's bigger dimension to a smaller dimension, right? He's doing. So what he did, he just took one orthonormal basis of M dimension. You can take some D dimensional also, some bigger dimensional, okay. And from that, so what he did, he just took some subspace, okay. So B is a subspace, and okay, so this is all a not orthonormal basis. Why he took orthonormal basis? Because all the others should be perpendicular to each other, and we need only the direction, okay, right? So the direct, or you can say in this way also, in the subspace generally, in the what you can say in the basis, generally we need the direction of the vector. So it's like the product, like the magnitude of that should be one, right? So that's why he took this orthonormal, so it can like satisfy both the condition that the perpendicular to each other, all the others will be like all the this M vectors, whatever we are taking, will be perpendicular to each other, and the what do you can say, the magnitude of each vector should be like, it will be one. Okay. So what he did, he first chosen M. Okay, so you can do with D also, like he did in the same thing in the end. Okay, so he took some B and then B dash. So what he has done, if I'm having, for example, I'm having this as a what you can say subspace or basis. So with this basis, I'll be able to know, like I'll be able to convert any vector in this form, right? The linear combination of this basis, right? So this is what he has done. So for all the cases, for all the eigenvector, he has just took some constant alpha I, and so linear combination of this vectors, like the vector, the orthonormal vector, that whatever he has chosen. Okay, so he has converted all the vector in that form. Whatever what are these vectors? So these are the data set we were having in the starting. Okay, so this is the original data point. And then we have to know regarding the projected value also, right? So we need to know regarding the projected data sets. Then only we'll be able to calculate the error, right? So this is the, I guess, the projected data set. So this is the projected data set, and how he did. So what he did, so he took two constant, I guess. One is the Zij and one is the Bj. So that he'll be in the end, I guess, he has to calculate the value of this G and this B also. Why he did so? This B will be almost similar to this constant B, will be similar to all the whenever he'll took the combination, like the linear combination, if he is taking, so this B will be similar to that of the earlier one, but this J will be a different one, because this I guess is coming from the B, this B, and the other one is coming from there, because in this we were having the subspace only M subspace, because M is the lesser number of dimension and D is the larger, like this is the dimension that we were starting with. So we have to go till M from the D. Okay, so this constant he has taken, this constant will be applicable for all the data set, and this constant he has taken for only for that M subspace. Okay, so then he has calculated the reconstruction error. Okay, this is a bit difficult to understand, but if you'll go through maybe that book, that will help you. So the variance part is like, if you'll try to go through the variance one, that is pretty simple. So that in that variance one, you can go through that simple dimension also, like 2 dimension, and you have to convert that into 1 dimension. Okay, so that maybe that will help you to understand how is it going. So here what he did, he just calculated the minimum squared error. So squared, and then he used some basic maths tool to conclude this. Okay, so that some cases he took C1 into U1 plus U. So if this is the case, and U1 and U2 are orthonormal to each other, so this will be in the final result of this equation will be C1 square plus C2 square, because all the U1 and U2 are perpendicular, and U1 is the magnitude of U1 is also 1. Okay, so this is what I guess he has kind of concluded. So he has just written the xi tilde from here, and after that he has from here to here he uses this case, like this method I guess he has used to conclude here. Okay, so from this when he was calculating the minimum squared error, from minimum squared error he came here, and then with help of I guess okay, now what happened, now he has to know regarding the G and the B, okay, because he has to calculate in the end, right? Because he just took some random variable in the starting and P. So what he did, he just differentiated with respect to, I guess, whatever he was needing, like he was needing J, G. So he has done the partial derivative with respect to G to know the value, constant value, that G. And then he has done, so I guess in the Lagrange method also we do the same thing. If I'm having two variable, so I'm doing the differentiation, partial differentiation with respect to G, and then he did with respect to B to get the G. So G is simply this Xi transpose U J, and B would be all so similar. Okay, so B is similarly the X mean value. Okay, so this, so what you'll do in the PCA when you'll start doing the coding now, so first thing you will do is to do this, you will do the whatever the data that you are having, right? So what you will do, generally you would have studied the stats that you generally do, that standardizing of the value or the whatever the data set you are having. In that, what you do, the variance should be 1 and the mean should be 0, right? So here the mean, what you are getting, the B, you are getting in the form of mean, I guess, 1 upon n summation of xi. So in later part, you will know this is not going to help. This is not going to help in either way, right? Because before the data set, I got the data set and I just standardized all the value. Okay, so B is not going to help you because X transpose will always be 0, because we have shifted the data, like the mean of the all the data set to the 0, right, and the variance to the 1 of all the data set. So this is not going to help. So in the end, he'll just take this X transpose X mean as 0 to prove in the end. So X tilde, now X tilde we have already took with G and B. So he has just intuited or kept the value of G and B here. Okay, so this is the method, and yeah, X trans now X bar is 0 because already in the starting we did the standardization of the data set. So this will be 0. So we are left with this value only. Okay, so after that, what he did, so now from here, so X tilde is this one. Now he has calculated the reconstruction error. Again, he has calculated. Earlier, we were not knowing the G and the B. Now he's already aware of the G and B. So after getting the value of G and B, he kept the value of that. And then he get, I guess this is, yeah. So this is the error that he's getting, Xi minus, this is the original data set and the projected data set. Now the squared it, okay, so okay, so this is the simply the optimization problem that you have to solve. So this is the error that you have to solve, the error that you have to minimize. Okay, so now you have to get the optimal G and B, the squared it. Okay, so this is squared. After putting the value of G and B, you are having this error. J generally represents the error or whatever the reconstruction error of those data set. So now we are left with this generally is getting converges to that covariance matrix, that if you'll go from the variance method also, you'll see that in the end, after doing that Lagrange multiply, like whatever the term or whatever the concept you are using to conclude the final thing, you'll see that in the end, again, you are getting the covariance matrix, right? So in the from the reconstruction error also, you are getting this covariance matrix of the whatever the data set you have, right? And in the next, so I'll complete this and then you can ask the doubt. So what he did, so now you're having the covariance matrix. Okay, so now, so why, so you were having this covariance matrix as U transpose C. Okay, so why he did add this lambda? So this why, I guess, okay, so this lambda has been added. Okay, so earlier what we were having, only So earlier what we were having, I guess, okay. So earlier I was having only U. Okay, so I was having only this, right? That will vary. Okay. So this is what we were having in the starting. Now with the help of Lagrange, we have added lambda also. So why we have done that? Mhm. Okay. Okay, yeah. So that was our yeah. So this is the because of the constant we were having. So we were having the optimization problem as two. We got that that covariance matrix, okay, or the reconstruction error, whatever it is called. So that we have to minimize with some constant. Okay, so that what is that constant? So the constant is that if you are having this U transpose CU you are having, right? So C is the covariance matrix. So this U, the magnitude of this U should not be greater than one. Like it should be one. So this is what the constant is. Okay. So U transpose U should to minimize this U transpose U equals to satisfy this problem also. U transpose U should coming to be one only. We are using this lambda term. Okay. Are you getting, or I guess you slept?
A little bit, sir.
So can you say, because that second portion is not that clear.
Sir, can you explain it with an example? I mean,
Sir,
This proves like
I
can't take any example, I guess. Oh yeah.
sir, I wanted to ask that how important is this is understanding this proof going forward?
Like the basic maths you already know. Why are we doing
Hmm.
this, right?
Right.
This proofs and all is what it's not that important, because whenever you'll do a code you'll not require anything of this.
Hmm.
You'll just need, okay, I'm having this 1,000 features.
Hmm.
How will I have to visualize this, I have to reduce the features, so I'm having this 5 methods, dimensional reduction method, so I can just apply PCA with one line of code. So I already know how does that PCA work. The proof and all is like how we are getting is not important. So why and what we are getting is mostly important. If you are not doing any research in machine learning, are you getting like, so
Okay.
if somebody is not doing research in this field, I don't think so this is like much important to know like how we are getting this, how we are getting this eigen value or eigen vector in the end. We already know if somebody the basics like ML, I don't think so anybody would be aware of, like most of us, even I was not aware, like I did some courses in IIT Madras. Like I generally passed out in 21 from IITM itself. I did some courses from Arun, Professor Arun. Like he generally teaches very like nice. From next week, you'll know regarding like from next, I guess 3-4 week, you'll know the how to solve the optimization problem. So when he'll go through his lecture, you'll be like he generally teaches very awesome. So I told you to, if you want to know regarding the PC also, you can go through his lectures that I requested them to upload. So they uploaded that video on the YouTube, like that has like anyone can now watch that video. So I'll paste it, that link, they can go through that. In that paradox, if somebody would have attended his workshop, he can say like he generally teaches very nice. So if you'll go through, you'll get some idea how we are like why we are doing this piece. But basically, if somebody is very new, it's like the proofs and all is not important at all. Okay, so why and how, like what are the final result, whatever I'm getting is pretty important. How we are doing, it's very vast also. Like many of the person generally doesn't understand this school read these books and all to know. Like nowadays, like if you know, if somebody has just told you what is that piece, you can just Google that and you'll know okay, how does it work, basic maths, and then you'll be able to know the library, which library to use for the working of the PC, and you'll be able to do that in a minute, I guess.
Right.
Yeah.
Thank you, sir.
Yeah, so okay, so yeah, the Preetodip, I guess, is uploaded, like not uploaded. She just posted the link of that video, I guess. Yeah, this is the video. If you want, you can go through this. maybe that'll help you. Okay, so what is somebody else?
So the constraint that over here it is U transpose U should be 1. That is that the constraint is that these two should be orthogonal.
This this yeah. So the thing is, U transpose U is not ortho. The if some one vector is having magnitude at 1, how generally you write that? So that if that vector into that vector transpose should be equals to 1, right? If because I told you in the starting, I need the direction only. I don't need the, anything else. I need the direction where the reconstruction error is minimum. So to know the direction, I can and I just need the unit vector in that direction. So for unit vector, the important thing is that the transpose of that unit vector should, like, if the magnitude of that unit vector should be 1, so that U squared is equal to 1. So U squared, then how you write in the vector form, U transpose U, right? So U transpose equals to 1. U
Yes,
transpose U should be equals to 1. So this is the constant. If I'll not apply this constant, that vector can be of some multiple times also, right? If
Okay, sir. Okay, sir. Understood.
that's why I need that constant to be applicable here. So the one thing is U transpose C should be minimum, and the constant should also be applicable. So for those cases, we are needing this mathematical term, I guess, Lagrangian, to solve this problem.
So constant should also be applicable. What does that mean?
Constant should also be like this condition should also be satisfying when when I am solving this optimization problem. This is our problem that we need to solve, right? In the PCA, this U transpose CU should be minimum, or the simple thing, the variance should be maximum, or the error should be minimum. So I have to solve the problem, the error should be minimum. And while solving that problem, some conditions are there such that U transpose U, whatever I need to know regarding the U here. So I have to solve this equation, U transpose CU should be minimum. And while solving that problem, I need to get I need to get U, right? And that U should satisfy some condition. What is that condition? That U transpose U should be 1. The magnitude of that U should be 1. Okay, so we are solving this problem. And while solving this problem, there are some conditions that we are applying on that thing. Okay, so that condition is U transpose U should be 1. This problem generally, whenever you read that gradient descent, other problem, there are so many methods to solve the optimization problem. Okay, that maybe next week is there to solve how to solve the optimization problem. So here basically we are using some maths to solve this equation. All totally maths we are using it. Okay, that's why it's becoming too heavy. But we do have so many other algorithms that we can write in like some lines, and that will solve us, that will do our work. Okay, so that algorithm will work for me. So we don't have to every time solve this bulky problem. Okay. Is it fine?
Yes, sir.
Yes, sir.
Yeah. So what was your doubt? Like someone else was asking. Okay. So this is the problem that we have to solve. And this problem is generally solved with the help of one mathematical thing, that is Lagrangian multiplier, maybe that you would have learned, I guess, in class 12. Generally, we read this. So this is having two variables, this U and lambda. U, that U you have to calculate. So what he did, just did the partial differentiation with respect to U and I guess lambda. And after doing that, he got this equation, Cu equals to lambda U. So Cu equals to lambda U is what? Generally, in the eigenvector, when you solve to eigenvector, what generally you get? You generally get X equals to lambda X. That if you are using that matrix, so what is the scale with that matrix has got skewed up, right? So here also, with the lambda scale, that matrix has been skewed. Okay, so this simply the final equation that we are getting, Cu equals to lambda U. That this is what, like, this is generally we I guess, okay. Okay, Cu equals to lambda U is simply the, if C is the matrix, so C is what? The symmetrical matrix that we are getting after calculating the covariance matrix, right? So this will work as a that generally you solve for that eigenvector, right? Ax equals to lambda X. Okay, so X there is the X is the variable that you need to calculate. So here it's you use that vector that you need to know with the magnitude should be 1, right? And lambda is the eigenvalue and the u is again the. So this is the equation that we generally solve to get the eigenvector also. And this is what we got in the end. So what we got in the end is this eigenvector corresponding to this lambda. Okay. And then I guess, yeah. And then he told regarding like if you are having some d lambda. Okay. So that d lambda. So this I guess I told you in the like last session also. So if I'm having d lambda, so if that lambda is 1 is the biggest, so the lambda, if the eigenvector corresponding to the biggest eigenvalue will be the 1, that will give you the direction with the maximum variance. Okay, so let this what is that? Okay, corresponding to the eigenvalue. So if you are getting, because you were having some d, if you are having in the starting you were having how many dimension you were having, d dimension, that you have to change it to m. Okay, so now if you are having some d dimension of the rectangle or the square with some d dimensions, you'll be getting some d eigen values also, right? And if you have to convert that into m, so you'll just take those biggest m eigen values only. Like if you have out of 10, if you need to take only 5, so you'll be taking all the 5 which are the bigger. So lambda, if I'm just arranging from lambda 1 to 10, so you'll just take from 1 to 5 if you want to, so if you want to convert that 10 dimension to 5 dimensions. Okay, so this is the basic steps that you'll be doing if you are if you want to do in the Python. So in the Python, if you are able to calculate everything, like you have calculated them, like you were having you just loaded the data set in the Python, you calculated the mean value, you calculated the covariance matrix, and then you have calculated the eigenvalue of the covariance. And what you have to, if you want to change that 5 dimension to 2 dimensions, so what you'll do in the Python, you'll just put that, so that you'll just need that lambda 1 and lambda 2 is the biggest one. So with the some basic loop and all, you'll be able to know which one is the bigger, lambda 1 and lambda 2, and then with the help of lambda 1 and lambda 2, you'll be able to like suppress that d dimension into 2 dimensions. Okay, so this is the final method. Like if you are asked to calculate like this, there is not much difficult question in the practice and graded, because we can, like, there can be some pretty difficult questions and all that is very difficult to solve mathematically, because we don't want to do that, because we already have all the algorithm, all the things that will be able to solve with some 2-3 lines of code. So why to do with the hand, why to solve mathematically every time? So what are the questions we are having? Those are pretty basics, only to know whether you understand the basic maths behind the PCA. That's it. That's why very less questions are there, and all the questions are very like simple to solve. Okay, in the exam also you'll get some basic questions only from the PCA, which already is a bulky, like nobody can ask difficult, because it will take whole like time to solve some basic problem. If you have to convert that 2D into 1D, that will take you 10 minutes to solve. Okay, so this is the basic method. Like if you're having some data set, and then what you did from the starting, you just calculated the mean and then the covariance. This is the basic method that if you are having some data set, like if you want, you can, like, we can share some data set that you can try from the Python also, how to conclude with the Python. And then you'll see that with the help of some one line of code, you'll be able to do the same Python, whatever you did in the same line, 10 lines of code, you'll be able to do in the one line of code in the scalar. Okay, so this is one example that professor has did. Like if you're having this 3 data set you were having, and then from 2 dimension you have to convert that into 1 dimension. How can you do that? So 2 dimensions, I'll get 2 eigenvalues and then 2 eigenvectors. So corresponding to this eigenvalue, I'll be keeping the eigenvector, because this is not going to help us. I told you how much information generally we are able to conclude also. If, like for example here, if I'm having some, so there's a basic formula lambda, whatever the lambda you're keeping. So that lambda upon the summation of all the other lambda, so those percent of information you are able to keep when you are trying to convert those bigger dimensions. Okay, so this is what has been. So this is very, what is pretty difficult to understand. I can understand, but I will go through the video like this. Maybe 5 pages are there. You can go through that if somebody wants to. So where is that? So this B sub, I guess, what is that name of it? So this is only from 561 to 563. If you read 565 pages, maybe you'll be able to understand a bit more, because the professor, I guess, has referred the same book. Okay, so this was the
Is this book Gilbert's time?
this is not Gilbert. This is not Gilbert. This is some pattern recognition. What is that? This is pattern recognition with machine learning by Christopher M. Bishop. So this book, you already posted in the Discord. You can just download from there.
Okay, sir.
So page number also I noted down, 561 to 565. I guess you can just read those. If you want to, if you're not reading that also is fine. Like you should be aware how we are doing that. That's it. On the page now I do okay. 560. So this was the one thing that with the one approach, how will you get the eigenvalue and eigenvector? This is the one approach. The other approach is the variance one. Okay.
Sir,
Yeah.
sir, how to do the PCA in Python?
In the PCA, if you are having, see, this is the basic method, right? So you're having some data set, okay? So these are 4 or 5 steps that you have to do.
Yes, sir. Manually, I understand how to do, but how to do it in Python? I was trying to do the same in Python, writing the code and all, but the major problem was in physically, when I do the calculation physically, I keep the fractions as a fractions, but in Python, everything get converted into float, and it becomes very difficult to understand.
So whether it's in the form of float or in the fraction, how it is going to like.
For example, I tried one data, and for that the matrix was 8 by 9, 4 by 9 and something. But in Python it was like 0.888 something something. So first I had to convert the decimal into fraction, and then I have to recheck, okay, my answer is correct.
So you can just refer some, okay, I'll just go through that. You would have heard about the analytics. There's like some blogs are there that you can refer. Okay, so from end to end, some basic Python code you would have done. No, this is not the correct one. So the basic 5-6 steps are the same. So you, okay, tell me again. So if you are having some 4/3, you got like, so what was the problem you were having?
It was one of the problem in activity question. So it was like the matrix C that I got was 8 by 9, 4 by 9, 4 by 9, and 8 by 9. But in Python, of course, it will give me the same numbers in float.
So how that is going to have like, okay. So you are telling me the data set, like the final data set, whatever you get.
Yeah,
Those
C matrix that we convert, that we make. So that matrix I got got as 8 by 9, and I was just trying to do some coding in Python just to recheck my answer. So is there any way that we can keep fractions as fractions only in Python, not convert them in float? Like I really have to convert the float number into fraction to recheck my answer, that if I'm doing.
okay. Yeah, there would be some other way, like in the Python to convert that into. Okay. I guess last time we shared that one collab file where we did with the help of Python itself. But I don't know where is that collab file. Maybe we can share the same file with you. But if that was the case, I don't know how to do that. Okay. So what you told, you have to convert that basic float point into like fraction, right?
To recheck, to
So if you can, have you used the Google for that? Like maybe that will help you.
Yeah, I tried to Google that how to keep the fraction into fraction and all, but I don't know, at some point I got so confused. That's why I thought.
Okay. Maybe I'll search for that. There will be some method like this is a basic thing, I guess.
I will also search again and I'll put it on this.
Yeah. If I'll put it there.
Thank you, sir.
Maybe somebody would be aware of that, I guess. If somebody is aware of that, you can speak out, you can say. Otherwise, I'll search for that. How to convert that. But the basic, all the other methods were working, right? So whatever from the starting, whatever the data set you took, and to convert that into covariance and then calculate the eigenvector and all eigenvalues of that were working, right?
Yes, everything was working perfectly.
Only the final steps, right? Because sometimes what happens, many a times you'll see that many a times student, not student, the covariance matrix, if you are calculating, so you are able to hear me, right?
Yes, sir.
So some background music should be there, but I can't stop that. So many a times if you are able to convert the covariance matrix, many a times, many of the blog, you will see that the covariance matrix generally they calculate with X transpose X, and many a times they'll calculate with 1 upon n X transpose X. Okay, then you'll the eigenvalue will be different, but the eigenvector, because we are needing only eigenvector, because we are needing the direction only. Okay, so that is not going to help. See, the 1 upon, if you are calculating the eigenvector of some matrices that has been divided with n, you'll get some different eigenvalues, but the eigenvector would be same for both the cases. So there is a one error in our cases also. If somebody would have went to the tutorial, so there is some error in the tutorial also. So please don't solve this. Everything is fine in this tutorial. Only one thing is that whatever the equation we are getting, like if you are getting some 2 upon 3, so every time you have to multiply the 2 upon 3 to calculate the eigenvector. Okay. If you're not doing that, in the final, you have to do something. Like, for example, if somebody directly solving this problem, whatever I'm having, like, for example, so I was having some covariance matrix I'm having X transpose X. Okay. So whatever the eigenvector you have calculated, okay. So like, for example, you have calculated lambda 1, lambda 2, something. And if you have to calculate X transpose, somebody is calculating the X. So this is the correct method. This one. Okay. So you will get the eigenvector as same, but you will get the different eigenvalues. Okay. So be aware of this. So tutorial, I need to sort out that how to improve that, because whoever the person who has made the tutorial, we have forwarded that, like the file link. Okay. So that's why we have not able to correct that. But every time, if you are calculating the eigenvector of the covariance matrix with 1 upon n X transpose Xa, so you have to multiply this n every time inside and then calculate the eigenvalues. Okay. So to get the correct eigenvalue, eigenvector, you'll get the same every time, whether you are multiplying, because that is not going to help in the eigenvector. Okay. So anything else from this first 2 lectures? Anything, like somebody was asking anything? Okay. So I'll just go through the next one. Next part is also like, I know it's a pretty like very difficult, not difficult, but like the proofs and all of these things are very difficult to understand. Okay. So yeah, somebody has wrote this code. You can refer this. Lee John has wrote one basic code from fraction to, you can convert that this way. The Python. You can try this one. Otherwise, I'll also search for this some basic Python you can get from, I guess, Google.
Thank you.
Yeah. So I'll just go through the next part also. That is also very painful only, but I'll just go through this. So the second part is the maximizing the variance. Okay. So I'll just go through this part. I'll go through the book. Okay. So okay. So you were using, Madhuri, you were using that OneNote, right? I guess.
Yes, sir.
I downloaded that OneNote, but I don't know how to use that.
Sir, it is like you don't have to do anything. It's like Zoom
So
Zoom
OneNote we have
whiteboard.
to download, right? This is a basic application, right?
Right.
And then how will you use that? Like,
Sir, in my OneNote, I just have turned on the dark mode.
okay.
Just search here and in the search box. In the search box, dark mode. It will tell you how to turn on the dark mode.
There's nothing like dark here.
Dark mode. Okay, sir, I will search and tell you because I turned it on and I have forgotten now. How did I?
Okay. I just downloaded yesterday.
s-
I'm searching for that.
Sir,
Yeah.
maybe you can look in the view tab.
View tab.
Yeah.
Switch background. Switch
Page
background.
color.
Switch background.
Yeah.
Hmm.
Yes.
Like the whole OneNote, like this white tab can also be dark in the dark mode.
Mhm.
This is just the background is dark.
Yeah, this is awesome. Okay. So I read from one, like I took one course when I was in the IITM. There the faculty was using the same thing, and that was then I came to like I saw your like answer on that. Then I was like, how to use that. Okay, so I'll just go through the second part of that variance. So the first method is like the same, like both method will conclude to the same thing. Like you'll get in the end, you'll have to know the eigenvector corresponding to the biggest eigenvalues. Okay, so this portion I'll go through the book. Okay, so the book. So this is the maximum variance formulation. So here what he did, like you can do what, like if you are having some bigger dimension, d dimension, and the smaller, you have to convert that into n dimension. That is fine. But if you want to just convert 2D into 1D, okay. So here what maybe this is the pretty simple one to understand. So here what I did, like consider data set of observation xn, where like n is from 1 to n. Okay, so the number of data set I'm having is a bigger n. So xn is okay, this is fine. And our goal is to project the data onto a space having dimension m that is very less than d, while maximizing the variance. So we have to maximize the variance of the projected data. Okay. So how we have started? We have started with, to begin with, okay, consider the projection onto a one dimension. Okay, so we have to, so we are considering m equals to 1 here. So maybe that will help you to understand. So we are just converting that d dimension to one dimension. So I need only one eigenvector. Okay, so I need only one u. Okay, so we can define the direction of this vector using d dimension as u1. That is fine, which for convenience and without loss of, I don't know what is that. So we shall choose a unit vector so that, yeah, this is the constant, that the constant is like ui transpose u should be equals to 1. That is the constant that we were knowing from the starting, because we need only the direction. We are not caring about the magnitude. We are just caring that that should be a unit vector. For the unit vector, that u square should be equal to 1, and that gets converted to u transpose. Okay, so the mean of any, like the mean can be calculated. The mean generally doesn't help you either, because we already have standardized the value, standardized all the like that thing you are able to know, right? How to if you are having some data set, how will you do that? How will you standardize that data set? So you already aware of that, right? In the stats too, maybe you have how to do that. You just have to, that the mean should be 0 and then the variance should be equals to 1. Okay. Yeah. So the projected data is what? The projected data, if I'm projecting, so I was having that. Okay. So if I'm able to write it here. Okay. So I'm having this. I was having this features. So it's having so So I was having this features, okay, and this direction I was needing. So I was having all the data set. So if I need to this is the direction, this U also. If I'm projecting all the data sets, so we are getting this U transpose X, right? Okay, this is for the mean, so we are writing X bar. But if I'm projecting all the data set on this direction, this can be written as either you are writing this as U transpose X into or upon this UI ka whole square. Okay, that is one already. So the transpose data set I'm already having. So what you have to calculate in the variance? So you have to calculate, how will you calculate the variance generally? You calculate the variance as 1 upon n, and then the summation of all the data set xi minus x bar whole square. This is how generally you calculate, right? The variance. So this is what has been calculated. So xi data set. So xi, what is the data? So now we are having the mean as this one. Okay. So this is the mean. Okay, that is fine. The variance of the projected data set b. So this is the projected data set, and this is the projected mean value. Okay. So this is the projected data set whatever I'm getting. So UI transpose X is the all the projected data set on this U direction. Okay. And this is the projected data set on mean direction. That's the mean of those values. Okay. So where is it? Yeah. So this is the mean that we have to can be calculated if we are transposing the mean of X onto that U. So generally you calculate in the same way, right? The variance also whatever you read in the stats part to calculate the like the variance, the spreadness from the mean value. So this is what has been calculated here also, and this is what has been written in UI, S and UI. So from the reconstruction error also you were getting the same thing. So to minimize, so what you were getting there, so the same thing now you are getting here also. So with UI transpose S UI you've got S is similar to the covariance matrix that you will get from the data set, whatever you're having. Okay, the same thing now you're doing. Why? So why we are doing again? You are using the same Lagrangian multiplier. Why? To just use the constant term also. So the constant is also important because you have to solve this optimization. That is fine, but you have to use this constant should also satisfy. So you have to like this problem you have to solve, and while solving this problem, this condition should be satisfied. Okay, this problem you have to satisfy. This UI transpose UI should be equals to 1. That's why you have taken again with the help of some mathematical tools like Lagrangian multiplier. He just converted, so differentiated. He would have done the differentiated with respect to UI to get this. And this is again the same thing that we were getting from the reconstruction. So this is a pretty simple one to understand with respect to the reconstruction error. The final result is almost same for both the cases, but whatever the result we are getting is almost same. So again, we are getting the same eigenvector, okay, corresponding to this S matrix. And S is what? S is the covariance matrix, okay, of the data sets, whatever we have. Okay, so this is a lambda. Lambda 1 correspond to the biggest. If I'm converting this into only one data set, so lambda 1 correspond to the biggest eigenvalue, and U1 will correspond to the direction. That direction corresponding to the biggest eigenvalues. Okay. So the final result you are getting from both the equation, you are getting the same thing. That is the eigenvector corresponding to the biggest eigenvalue. Okay, the same thing I guess the faculty has also taught. So the same, he has to maximize this and to maximize this with this constant U transpose U equals to 1. He has solved this equation with the help of some Lagrangian multiplier only. Oh, okay, so he has used some different mathematical tools to solve this, and in the end he got the same final result, Cu equals to lambda U. Okay, then what is that? Okay, and with the help of same example he solved, and he got the projected, like the final projected value or the whatever you have to calculate. So he'll be able to calculate that. Yeah, now I think so. Maybe it would have helped you a bit, but I don't think so it would have helped you much because it's a bit complex to understand also.
Excuse me, sir.
Yeah.
Can I So again, this is just regarding my understanding of the topic. So it is basically concept. It is not related to like anything input, like it's encompassing the whole thing. So can we say that the variance that we get, right? The so-called variance, that is basically um, the reconstruction error. Like in a way, it is a reconstruction error of a well-balanced or a well-centered data set.
Yeah.
Is it?
Yeah, because the variance also we are doing the same thing, right? So we are just from the mean value, like calculating from the mean value, we are seeing the spreadness. And the reconstruction error, we came with the, like we started with minimizing the error, but we concluded that in the end we are getting the same matrix.
Yeah, because basically looking at if you have a certain set of data points and you select those lambdas or those eigenvectors which has the maximum influence or the maximum lambda on the data set, then we are looking at how much of a difference the scaling with regard to the say the eigenvectors that we choose for dimensionality reduction is with respect to the original data set.
Yeah.
Yeah, I just wanted to like understand if my understanding that was good.
Yeah. So have you went through that book also, like that 4 or 5 pages? I guess.
Yes, sir, yes.
It is almost same, right? The whatever the professor has, right?
Yes. I think we like talked about that.
Yeah. So your name, what's your name? Like good name?
My name is Lee, sir. Lee Jones.
So where are you from?
I am from Kerala.
Okay, Kerala. I was there in Kerala. I did some project in Kerala. Sri Chitra. Have you heard of that? Like medical college? Sri Chitra. Sri Chitra. Have you heard of that? That is in the Trivandrum.
No. Okay, I am not near Trivandrum.
Okay.
I am
That's
in
the one like biggest hospital for the heart, I guess. But I'm forgetting the name. Too. Like I went there for one ML project only. I used to like collected the data like MRI of some Alzheimer patient, and then I worked on that.
Okay.
Yeah.
So it is like systems. Is it systems medicine?
It was a government, like I went from IIT Madras itself. What you are asking?
No, I was asking like was it like related to systems, because we are having that this thing right over there. We have an interdisciplinary department, right? That
this college.
Brain, computer brain. Okay, Sri Chitra. Yeah. Okay, this is famous. Yeah.
Yeah, this one. Yeah. There only I worked for. I not worked for. I was having the project for 3 months. I went in from the IIT Madras itself from the last semester, I guess, when the COVID was going on.
I live near like I don't know if you have like Kusat, you might have heard, right? Like Deepak sir.
Oh, okay, Deepak. Yeah. So he read from QSET only.
Yeah, I know.
Yeah.
So I live near that.
Okay. So you're from QSET only?
No, I'm not in Kusat. I'm like my house is nearby. That's
okay. Your house is nearby QSET. Well, the QSET is mostly famous for, I guess, that marine engineering, right? Mostly.
Yeah. They have a strong department in marine engineering.
Okay. So anybody else? Like this topic is like complex. I don't know. Like Yeah, every time people generally face problem. Like even us, like whoever is the instructor generally faces the issue in this topic. SPD, PC and all. And after that, it become very smooth. Like after this week, I don't think so. Will need us also. So we'll just go through the lectures and we'll be able to understand everything. Maybe in the last week, a bit complexity is there. But other than that, everything is fine after this week. That's why earlier this all things were in the 6th week. So we have split it to give you more time. So that will make, like last term we were having very like this term we have just split it so that we feel like we have increased the number of sessions also. Last year we were having only 2 sessions. This year we are having 3, and then again sometimes we are having 4 sessions now. So I guess on the Sunday also there is some session like this. You would have got the announcement, I guess. So Abhinandan would be taking that.
Yeah. 3 to 5.
3 to 5 Sunday, yeah.
So again, regarding this covariance, right? The
Yeah.
covariance matrix. So with relation to SPD,
Yeah.
like you have, let's say, Q1 times sigma times Q2 transpose, right?
Yeah.
So can we say that SVD that sigma times Q2 transpose is similar to the the covariance matrix?
The covariance matrix, whatever you're getting, is similar to, yeah. So see, in the starting, we were having some M cross N matrix, right? Like for example, I'm having some data set of 60K into 786, right?
Yes. The original one.
Yeah, original one. So in the end, we have got some covariance matrix. So that for those cases, we have to calculate the eigenvalues, right?
Yeah.
That is what that is similar to that A transpose A, that because A transpose is also symmetrical, and that covariance matrix, whatever we're getting, is also symmetrical.
Yes. So that is basically the sigma times the sigma times, not sigma times, but that Q2 transpose is similar to the eigenvectors of the covariance matrix.
Yeah.
Sir,
Yeah.
sir, I found the option for dark mode.
Okay.
Can you please open the OneNote? OneNote. Yeah.
Where is that? Here it is.
Yes, in the file. So in the file, you go to options. Option in the last.
Okay.
Yeah, in the option you go to office themes. Here, office themes. So in that, office theme, in that select black.
Okay.
Okay. Now it is the dark mode.
Okay, thank you. Where is that? Okay, no, I got right also. So this is to write. This is the one. Okay, this is the pencil. Okay. Okay.
Yeah, you can make your own colors and all.
Yeah. So does anyone uses event, the event note also? Event, or what is that event?
Sir, Evernote. That's
Yeah,
Evernote.
Yeah, Evernote. Does anybody use that? None of you. Okay. Like I'm learning how to, like I'm making some notes in that, but I don't know how, like I'm just making in some bad math, like
So
bad
why
way.
don't you go through some YouTube videos? They'll guide you through that.
Yeah, I went through that. That is how, like with the help of those videos only, I'm able to do this at least.
Sir, I would suggest you should try Notion. Notion is the new organization software.
Okay, that Evernote generally help us, like if I need to make some notes for one particular topic, I can make, right? I don't know Notion. Okay, I'll search on that. But this I look like the
So you
Evernote.
can do that in OneNote also. If you want to make it, like you can make some sub pages. You can also
Not in
organize
writing.
there.
Can I take, like in that?
You can
Can I take
write
this
if you have a
thought?
tab. Like I write my notes on OneNote. So if you have a writing pad, then you can use that and you can write. Like I have made my machine learning topic in one, and then I have subgraded assignments. If I'm writing something from somewhere, then I have made some sub pages also. So you can make topics.
So everything is in
Also.
the writing form, right?
No,
No,
you
sir.
can.
You can also text. You can also use text. Like you have to select whether you want to. If you go to draw, sir. If you go to draw, then you can write with the pen, tablet, or whatever you have. Like if you have a Wacom or something. Otherwise, if you don't want to like write it with the tablet, then you can use the select something is there. Like I have used both. Like if I'm making some notes from a book, then I just copy and paste it over there. So that's a written thing. That's a typing thing, and the other I make it with the writing pad.
Okay.
You can do that in OneNote also. That is also quite organized.
And sir, you can directly, like, if it is more convenient to insert pictures or insert
So
links,
that is what I need. Yeah.
that
Yes,
can
sir, that
happen in
too.
OneNote.
OneNote,
Okay.
yes, sir.
Insert with the insert option. Yeah, in
So
that
shall I
screen
show you
clipping,
how you can
pictures,
write also?
screen clipping, pictures. You can take anything. Screen clipping will basically take whatever on your screen, take a picture, like
I
screenshot of
generally
that.
use this one. Like this is the snipping tools, and then I take the screenshot. I put it in the Evernote.
Ha.
That is what I am doing now.
Okay, okay. But for in this is the built-in feature.
But
Feature.
the thing is, in Evernote, you can't write with your hand.
Yeah, right.
Here you can write, I guess.
Correct.
Okay.
And pictures, meaning you can insert some pictures of your own.
Yeah. So this like I made for some. So this is what I'm doing. I made for only 2-3 days, but that I need to make for some like 5-6 months. Okay, I'll try with that. This is good, yeah. This looks fancy also. Yeah. Okay, so yeah. So what else you have to discuss? We are just discussing.
Sir, can you suggest us some like steps that we can follow to like build all these things, all these concepts? Because like people for me, like I'm very new to all these things. So if there are certain process or steps that we can follow to build our concepts in machine
in
learning.
ML only, right?
Yes, sir. Yes, sir.
Okay.
So because the sources are very scanty, like you don't get it over on YouTube. Like the resources are actually very limited for this.
Have you done that SQL first? SQL have you
No,
learned?
sir. No, sir. I have TDS, MLF, and PDSA.
Okay, PDSA is good. MLF, fine. TDS, what generally you read? Like, okay, tools in data science, right? So what are you reading in that? Tools in data science? What are the
So we are doing
topics there?
scraping, cleaning, data cleaning, scraping,
Okay, that is good.
regression.
Okay. Yeah, those okay. So how generally I learned the SQL first, like when I was in the ITM itself. I learned SQL that you'll read in DBMS, I guess. DBMS if you'll, I guess, next term, or maybe if you'll, but SQL doesn't take much time. Like, it will take you like 5-6 days to learn SQL, maximum 5-6 days. That generally helps to know the basics things. Okay, and then in the the 4-5 terms like pandas, numpy, and all. Python
Yes,
you
sir. Yes,
already
sir.
read, right? Python you
Yes, sir.
are.
Yes.
So you can just go through this 5-4 things, right? Maybe you can search on the Google.
No, sir. I'm not talking about that. I'm talking about the concepts. I want to build the concepts like PCA or SVD, whatever is there. Like because the
Okay,
resources, like after I had a talk with you, I understood how SVD and PCA is related. But before that, it was like very confusing to understand like what is happening, because that is also reducing the dimension, this is also reducing the dimension. So what is actually happening? So
okay.
if
But
there are
those
certain books or tutorials on anything that we can go through.
tutorials are not like there is not like compiled thing at one places. Like you can go through Max and Gilbert book, but that book is also very some chunk of things you can go through, or
So
you
that
can go through.
Howard Anton by linear algebra, elementary linear algebra, is that good?
I didn't know about that. Like that would be a very famous one, but I didn't know about that. Uh, this Gilbert lectures is also there. Maybe that will help you. The 2-3 lectures you can go through. That there are, I guess, lectures on by Gilbert. but that is also like more theoretical, I guess. This 3-4 top,
So
like from
Gilbert is not very student friendly. It's a little difficult to grasp
yeah.
those things.
Yeah. So 1-2 topics you can see, like SVD, you can go through that. SVD or definiteness, you can read. If you're having linear algebra, some 4-5, like for the linear algebra, there is one on the YouTube. There is a very awesome some lectures. I don't know, I can't remember that. Okay, I'll just search. I'll tell you. But that will help you to know the basic understanding of the matrices. First, you should know the basic how that matrix, why we are representing all the data set in the form of matrix. Okay. So the
Talking about 3 blue, 1 brown.
yeah. That is really awesome. You can go through that. 5-6 videos are there. If you yeah, this one, blue, 1 brown, I guess. This from some 7-8 videos are there.
But sir, that was good till maths 2. Because
Okay, so you
now the
already have
things
seen.
are no, yes, sir.
Okay.
I've seen almost all. Even Khan Academy gives the mathematical background, and 3 they give a visualization thing. So
Yeah. So after that, so if you are aware of this, so you're almost aware of till week 4-5. Okay. So now you're left with only PCA. So the PCA, okay. So PCA, one thing you should go through the professor like Rajkumar, that video one, like Arun Rajkumar. If you're not able to understand from that, like he has explained a very beautiful way. One more thing, I don't know I should say or not, but that is that I if you will mail me, I'll tell you. Okay, I don't know where here I should say that there is, because those are like some private institute and all. So those are having some good lectures. You can go through that. Okay, I'll just, if you'll mail me, I'll just tell you. Okay, there.
okay, sir.
Okay.
Sir, I guess you can drop the message in chat box, whatever institute you are talking about.
Yes. I don't. Okay, I'll just, if somebody mail me, I'll just tell you there. I don't want to reveal the name. Okay. So this Khan Academy and all is very popular, we can say, but those are like not that popular. I don't know. There's a one
So, but
faculty from
Khan
IIT.
Academy was good till maths 2 or stats 2. But after that, when we are in diploma, they do
There
not
is
have
one
all those.
faculty from IIC Bangalore. No, IIC, yeah, that Bangalore. He generally teaches very good. Like, there are some lectures. I'll tell you. I'll just tag that video. Okay, there. If you'll mail me, that will help you to know the PCA part. Again, because SVD part, if you want to know more about that SVD, I don't know SVD. Generally, there is. I went through that. There is not much videos on the SVD, because those, wherever you will find the bulky maths part, you will not get the lectures, because those are the part of research. If you want to know regarding the coding and all, everybody generally will give you everything. But if you want to know regarding the maths behind anything, the bulky part, nobody generally like know much. Even someone is very like good data scientist in some bigger like Amazon, Flipkart also, will not be aware of the bulkiest, how the algorithms, the basic PC is pretty difficult. Okay, SVD. If you want to know regarding the maths behind the lean, like all the algorithm, other than this, like there are some algorithms, those are bulkier, like these are bit bulkier. But if you want to know regarding logistic or the SVM, like SVM is bit bulkier, but logistic, linear, or other the decision tree, random forest, and all. So the maths behind those algorithm is not that difficult to understand. So anybody can tell you. You can find on the okay. One more is that square. What is that? The name. Somebody is know about the stat quest. I guess. Yeah. So this is also
Yes, sir.
good.
Yes, sir.
This is also good. You can go through this also if you are able to. The PCA part is discussed here nicely, so you can go through this. Okay, so by George Stammer. Okay, this is also fine. You can go through this. Somebody has posted on. Okay, yeah, this is also good. Yeah, I know. So this, if you want to go through that, there are some lectures. Like if you want to know regarding the algorithm also, he generally teaches in very awesome way. Like this guy. So the PPT, whatever he'll use is like most of, whenever I went through many lectures, the person generally uses the lecture like the slides of this guy, Josh Stammer. Okay, so this also can be very useful for the PCA part or SVD. But optimization problem, Professor Arun, I don't think so. Nobody will teach better than him. So you just have to go through this Professor Arun video from next 3-4 lectures, 3-4 weeks. His video is the most awesome. Like I read with so many faculties in my life. Okay, but he was the best. I went like I used to go in his classes regularly. Like most often we generally don't go to the colleges and all, like in the class, but his class was very interactive and very awesome. Like so you can attend next 4, I guess, week 8th, 9th, 10th, 11th, yeah, 8, 9, 10th. So you'll not feel that you need any like other sources. So for this PC and SBD, you can go through this parts, and then next for the algorithm also, if you need, I can refer some, like this is also good. These are the free sources. Okay, if you want the paid one, you should not buy that. Like already you are like this courses MLF. After that MLT, like those courses are really like, all those courses you'll understand all the algorithm and all. Okay, so already you are having much, and this ML and all is like many a times you need to walk from yourself also. Like you have to go through many blocks, and because every day nobody can teach you everything in 12 weeks, right? So every day some new algorithm is coming. Okay. So you have, like I told you, like this, we are not covering when the modern, like whatever the things we are using nowadays. The PC has been developed in 1950s and 1960s, that we are reading now. So the newer one, we are not even touching that. Okay, that some more, if you just go through PC, there are other methods and all. You can, so this is the basic one, that the math, you should be aware of the basic maths behind the PC. But there are some others that should not be aware of those, like maths behind. You should be able to use those things. Okay, so if you are having some this type of data set, which algorithm I should use? So those things you should be aware of that. Are you getting my point?
Yes,
I guess everybody slept or what. I was
No,
having
No, sir.
this is a night, like we already had done the dinner. I guess this is the time for most of you. And also,
also
yeah.
this there's this guy called Steve Brunton or something. He also has a few good videos. Like I saw a few of his videos for this video.
Okay,
I mean,
which one?
just
You can put
Steve.
it in the chat box. Can you put it? So maybe, so there is one in the discourse also. One guy is like, okay, Steve Brunton. Is he generally upload videos on the YouTube, or is having some blogs? Or
It's a YouTube. He's
okay.
on YouTube also.
So this also, like everybody can search. If this is going to help you, you can go through that. So in ML and all, you have to research a lot. Like you have to, every day you'll get some new, so like algo and all. So yeah, this is what you have. If you are going to become a, like work in data science field only, so you have to, most of the time, like we also, like generally when I was doing the project and also, I used to code, like for even one line of code I used to do the Google. Every time I used to Google. Only Google was there, then only I was able to do everything. Other than that, nobody is able to remember anything, right? So it's very difficult to remember. You should be aware of what I should do here. That's it. Even the, like many times if somebody is asking also, he'll not ask you, he'll just ask you if I'm having this type of data set, what should do? Like if I need to, I'm having this outlier, what you'll do. You'll not ask the code directly, because if you know the method, you can just Google and you can know the that line of code. Okay. This also, this step Brunner, if this helping you, you can go through that. But this is the only 2-3 topics. Like after that, you'll not face much issues. I can guarantee that. But to know more about that, you have to scroll. Yeah.
But I think towards the end term and all, I think it would be a much more, and you need a much more higher knowledge, right? End term mode, like at least when you go for the courses that have MLF as a prerequisite, like MLP and MLT.
Yeah. So MLP and T is totally heavy coding MLP practices is totally like coding course. Okay, so you have to do one project also in MLP. So that project will be of like, today only we have decided that that will maybe not for you guys, whoever is in the MLP, that phase has been released today, like that course you have to do in like 9 weeks or 11 weeks. Okay, that you can do with the MLP itself. If you don't want to do, if you just want to read the MLP first and then do the project, you can do it in the next term also. Okay, so these are the things that the project you have to do, that will help you to work on some data sets. So you can start working on the data sets now itself if you are having time. If you don't have, you can wait and you can go through the MLT, the techniques one. The techniques will be knowing all the algorithm. Okay, and that algorithm you will be using. Apart from this algorithm, these are the basic algorithm. Okay, so you will be reading all the algorithm like logistic, linear, decision tree, random for all those SVD and SVM in the techniques, and that you'll using with the sklearn, you'll be using that in the practices. Okay, that is a totally in the MLT also. There will be some sort of coding, but in MLP only the coding stuffs will be there. Okay, then you have to do the project, and then if you are going to the degree level, you'll be having now next like September. There are so many other courses are getting released like NLP or deep learning or some pattern recognition in ML also. So there are so many courses going to launch in September. So these are the basic, like that's why I'm telling you the maths, if you're not understanding, that is fine. It's like nobody, I can bet you like even 100 people who is working in data science field, not even like 5 people should be knowing much about the PC and SU, how does it works. Like
you might, but you would still be needing it for like higher studies, right?
Yeah, for the higher studies, you'll be pakka needing this. If somebody wants to go and higher studies mean, I mean to say, if you want to do some MS or PhD in this field, okay, then you'll be needing. Other than that, if you want to go in some bigger companies and all, the basic maths only you should be needing. If somebody asking how does the PCA work, you should be aware of that. Okay, this is helping this in this. I need to know the direction of I know the direction where the variance is maximum, the reconstruction error is minimum. That is, and that I have to solve. That can be solved with the other algorithm, some gradient descent algorithm. There are many others. I can. So this is what generally, if somebody is asking. But if you want to do the research or publish some paper and all, you have to go through. You should be aware of all the things. Right?
Yes.
1 second. Somebody's calling. Yeah, so sorry for that. So yeah, so what we were talking, okay. So anything else, like any problem in solving the questions? I don't think so there will be any issue in solving the problem, right? Because the problems are pretty simple, I guess, right?
Yes.
So still, if you could work out one of those.
Okay. So which one? From the practice or what?
Yes, so practice only, as graded deadline is not.
Okay, I'll just go to the practice then. So upload it, right? So yeah, so earlier it was like it was in the 6th week itself. That's why in the PDF you are getting, so that I have to split and then I'll upload. But it's already in the, if you are going through the 7th week, it will be in the 6th week. So, okay, so this is the data set, right? This type of problem, I guess, would be there in the this week only. So if you are having this data set, if you have to calculate the mean vector, so mean can be calculated directly, right? Then you have to calculate the covariance matrix. So for the covariance matrix, this xi minus x bar into xi minus x bar, like you have to calculate the transpose of that. So if you are having some data set, like for example, xi you already have, right? 0, 2 or 1, 1 or 2, 0, right? So for each of the cases, like for I equals to 1, 2, here we are having 3 data sets. So you have to do it 3 times and that you'll do. So this has been done once, twice and 3 times. And then you'll be able to know the covariance matrix, right? And now you have to calculate the eigenvector. So this type of problem will be there only, right? So only the eigenvector, how you calculate eigenvector, you already, eigenvalues, you already know how to calculate that. So see, one thing you should not do is, if you are calculating the eigenvalues here, okay, so please don't remove this 1/3 outside, okay? So if I need to calculate the eigenvalue of this equation, if I'm having this one, 2, what is this? So 2 minus 2, 2 minus 3, I guess. No, not this one, 2, I guess this one. So if you have to calculate 1/3, so just do it this way. 2/3 minus lambda, minus 2, and 2 minus lambda. So 2/3. Okay, then calculate the eigenvalues. Okay. Then you'll get the correct eigenvalues. And then you can calculate whatever the eigenvalues you'll get. So please don't do like this, like 1/3. So you have just, and 2 minus lambda. You can do this, then you have to multiply that in the eigenvalues. Whatever the eigenvalues you have got, you have to multiply that. So you can do in this way. If you
So
are
we
doing
can
this,
do in that way, and then whatever eigenvalues we get, we will multiply it by 1/3. Is it?
1/3 or 3, that you need to check, I guess. I'm also not sure. I'll calculate. Okay, so I'll calculate now itself. So the values, whatever we're getting, is the final answer is what? C is the final. So 4. Okay, so 4/3. Okay, so you have to multiply with 1/3. Have you got the point? So if you are calculating, you are just taking this only, 2 minus lambda minus 2 and 2 minus lambda. This is what the matrix we are having, right? So if you'll calculate this, so what the value you'll get? 2 minus lambda ka whole square minus 4 equals to 0. This is what you'll get, right? So lambda
Yes,
is plus 4. So are we doing it correct, or minus 4 lambda equals to 0? So lambda, you're getting this got cancelled. So you are getting some lambda minus 4 equals to 0. So you are getting lambda equals to 0 or lambda equals to 4 if you are doing in this way, right? But this is not a correct way. So what you have to do, you have to multiply this with 1/3. So you'll get 4/3 as the eigenvalue final. So I'll just verify this with this one. So what I have to do, 2/3 minus lambda minus 2/3 minus 2/3 and 2/3 minus lambda, right? This is the equation we are getting if we are multiplying everything upon lambda 1/3, right? So this is 2/3 minus lambda ka whole square minus 4/9, right? This is what we are getting. So if we'll square this, lambda ka square plus how much we are getting? This 4/9 will get cancelled. So we'll be left with 2 into 2/3 lambda equals to 0, right? So lambda, you're getting lambda minus 4/3. So lambda you are getting here, from here you are getting lambda 4/3, right? So if you are calculating directly, you have to multiply this with the whatever the eigenvalues you are getting. And if you are multiplying in the starting itself, you don't have to do anything. Is it fine? So for this equation, I don't know in the final, like this is the wrong one. I guess we have already corrected there. So So yeah, we have corrected already. So 4 upon 3 upon 0. So earlier it was wrong, I guess. Is it fine? I guess Pulkit was asking. Okay.
Yes, sir, it's fine. Thank you.
Yeah. Okay. So this is how you'll calculate the eigenvalues, and then correspondingly you can calculate the eigenvector also. What is generally you have to calculate? But where it went here? Okay. So eigenvalues, eigenvector also you can, the data set, that projected data set, how you calculate that? There's a formula, right? You, that, what was that, like u, that x transpose u, and then x transpose you will get the magnitude, and then you have to calculate with this the same vector. Okay, so this is x transpose this u vector, and then again multiply with the u vector. Okay, so you'll get the projected data set, right? And you have to calculate the error. How will you calculate the error? Okay, so anybody is having an issue in this? And then to calculate the reconstruction error, what do you have to do? You have to the projected data set, whatever you're getting, and the starting data set. So each and every point you have to collect the difference and then square it to get the reconstruction error and divide it by the 3, because you are having, like if you are having n data set, divide it with the n. If you are having 3, then divide it with 3. Okay. Anything else?
Yes, sir.
Anybody is having any issue, you can ask.
So next week onwards, optimization will start, right?
Yeah, so those
That
will
was
be a bit,
earlier there in week 7 in last time.
yeah, it was last time it was in the week 7, I guess. Yeah, it was in the week 7, now it's in week 8. Now what happened, now we have merged the 10th and 11th week. 10th and 11th which are stats, related to stats, so we have merged those because you already have read, so you don't feel like you will not face any issue in those weeks.
Sir, is there anything special about the Sunday session?
Sunday session, if anybody is any doubt from like starting week itself, we can just, like there would be some Google form has been shared. You can just type the topics that you need to discuss and he'll discuss those topics. That's it. So nothing special about that. So the professor is not taking that session. Even from like our group, only one guy is taking that session. Maybe next, after that optimization will start, Professor Arun will take one session. Not, I guess, next to next week. So okay, that is done. We'll close the session, right? So the Saturday also we have one session. We want that session like that is solved with us, right? So okay, I'll just try to prepare some question that will not go much, like more than 1.5 hours. Is
Yes,
it
sir.
fine?
Be some
We start,
practice.
yeah, Saturday we have one more session.
Yes, at 2 in the afternoon.
Again, I have, I guess again tomorrow I have one session. Okay, then if everything is fine, like we'll close the session. Or if anybody has anything, any issue, you can ask me. And then regarding the source, if you'll mail me, I'll just write in the that from where you can take help if you want to. Otherwise, it's fine.
Yes, yes. About the PC, I think, right?
Yeah,
The
PC. Yeah. Okay, and thanks everyone. You can have your
Thank you, sir.
uh,
Thank you, sir.
Okay.